Good morning, everyone. This is the module one, and we are going to discuss about this mass transfer operation. In this, now I'm going to discuss about distillation column. So, in our first lecture, we will be considering the introduction to the distillation operation. Distillation is a method of separation of more volatile components from a less volatile one of the solution by partial vaporization of a virginal solution followed by the condensation. So, in this case, unlikely in absorption, we need to add some solvent, that is third component, to separate the gaseous mixture. But in this case, we need to have some liquid mixture, that is partially vaporized, and then the solution generated the vapor of the more volatile components, and then the components, some like condensation, it separates the mixture of components. That's why these distillation we do not use in any third component here. So we take this mixture and then we will separate them basically on its boiling point. Okay. So this is type of typical distillation column. Here we have some distillation is most widely used separation method for liquid mixture. So this is very widely used, and some of the example is, as we well known, very common example in organic process industries, like if we consider ethanol water separation, where we use distillation column, and another one is aniline and nitrobenzene separation in the process of aniline productions. For these production, we need to add some byproduct of nitrobenzene, and we have this to separate, and it will be done by distillation. So most common industries, as you can be different as you can use in different industries, most common particular like in petroleum refining. So in petroleum refining, there are plenty of applications of a distillation operation, and you should have huge plant for most refineries on the distillation columns. So coming to next, this is a typical distillation column as shown over here, and we can set just how to separate, how the operation is takes place in distillation column. This is a tray column that is shown here. So the tray column may be packed tower, but in case of tray tower, as shown over here, feed enters at some point of the tower. You can see over here, the feed is entered at some point of the column, and then reboiler heated up on the liquid from bottom of the tower, and liquid is partially vaporized. So we have a boiler here, which is shown over here, that is partially reboiler, and it is boiled up the liquid and then boils up, return back to a column. Then less volatile components, they come out as bottom. So reboiler heated up on the liquid from the bottom of the tower and liquid is partially vaporized. This is why, because here it is not completely vaporized. So vapor flow up through a tower or packing. If it is packed bed, it flows through the packing. It flows through the packing, and if it is a tray, it flows through tray to tray. So the vapor flows and the vapor leaves at the top and enters into the overhead condenser. So you can see here vapor is leaving at the top of the tower, and the top of the tower, yeah, we have some condenser type figure in this figure. Though overhead it goes to a conductor. So once you get into its condenser, a pot of condensate will be withdrawn. So the top product and the rest is fed back into the this column and as a reflex. So some of the part of these condensate which will be retained back to a column, and some part will be taken out as a top product and feed back to a column as a reflex. Now, what is bringing in this flow is gas and liquid from top and to bottom as a reflect, liquid as well as feed flow down and imitate contact between the liquid and the vapor across each tray or packing surface. More volatile components moves from liquid to vapor phases. So, though column and the more volatile components will move from liquid phase to a vapor phase, and less volatile components from vapor phase to liquid phase. So, mass transfer happens in both liquid to vapor and vapor to liquid. And concentration of these low volatile increases in liquid phase as it flows down. So less volatile components will increase in liquid phase down from top. The less volatile components will be retained in liquid phase. So next, and the vapor which goes up, it will be increasing, and the more volatile components. So the higher degree of separation of more volatile from the less volatile or reaches in this way. So the top product what we are having over here will be distillate is a more volatile component, and the bottom product will be rich in less volatile component. So this is the rich in component. So the top product distillate will be rich in more volatile component, and bottom product will be rich in less volatile component. So one, so there are some now distillation is an equilibrium stage operation. So as you can see, if there is any immediate contact between the gas and liquid and each tray, we can consider it is a reach the equilibrium between liquid and vapor. So distillation is considered is a equilibrium state operation. stage operation. So in this order, solution of the equilibrium stage problem, the vapor liquid equilibrium and the physical properties of the system are essential. So one is the vapor liquid equilibrium data VLE and the physical properties of the system. These two things are required to solve the equilibrium stage problems. The distribution of the component in two phases is governed by the vapor liquid equilibrium relation, and thus when two phases are in equilibrium, vapor liquid equilibrium data enhance you to use the relative and the composition of a liquid phase uh, um, to be composition of the vapor phase. So two phases, if we have related between vapor phase and the liquid phase, there will be an equilibrium. Then we can obtain a liquid phase composition to that of the composition in vapor phase. So here our um, so in our emphasis, it will be mainly on binary mixtures over here. So equilibrium data may be obtained by experiment, or it may be thermodynamic calculations or in published sources. So equilibrium data has to be obtained either we can get from experimental measurement or it can be some thermodynamic calculations. So it's tabular from as equilibrium diagram. So equilibrium diagram may take several forms. Those are TXA, temperature, pressure, mole fraction diagram, or mole fraction diagram, XY diagram, or HX diagram, like that. First, we will consider constant pressure binary equilibrium data diagram. So, if the boiling point temperature is plotted versus the liquid concentration x, then we obtain the bubble point curve here. So, in the top figure over here, you can see if we plot x versus bubble point, so we can obtain the bubble point curve. So this is the tx, the bottom curve red line over here. This one is the tx, bubble point curve or standard or saturated liquid line. Now, a plot of temperature and the equilibrium vapor composition, that is Y, is called dew point curve. In upper figure, you can see blue line over here, which is Ty curve or dew line dew point curve or saturated vapor line. So there is, as shown here, the y-axis we have bubble point or dew point, and the x-axis we have mole fraction x or y. A typical bubble and dew curve for a binary mixture is given in this figure. The figure shows common way of plotting TXY diagram. So we call it as a TXY diagram. With respect to the binary mixture, and all components are expressed as a mole fraction of the more volatile components. So these mole fraction X and Y is it represents the mole fraction of the more volatile component, not less volatile component. So the all component are expressed over in mole fraction unit. So X is liquid phase and Y in the vapor phase. If we know X and Y, we can also calculate the composition of the less volatile one by subtracting from 1. So 1 minus X mm, would be less volatile in the liquid phase and 1 minus Y would be more volatile in vapor phase. The lower curve plot the bubble point of a binary mixture as a function composition, and the upper curve is dew point curve. So the upper curve is a dew point curve and the lower curve is a bubble point curve. So for a given temperature and composition, these diagram, the what does it tells us means the nature and the composition of each phases of mixture that is present when the temperature and the composition is given. So from the diagram, you can tell the nature and composition of each mixture is present. So the nature of component as well as the composition we can tell. So at point L, given the temperature equilibrium concentration of A over here, you can see at the point L gives the concentration of A in the liquid phase X, and point G gives the equilibrium curve composition in Y. If we can join these two lines like 2 points L and G, we call it as a tie line. We can draw infinite number of such tie lines from these diagram. TXY diagram, a mixture on which the lower curve at point L at this one saturated liquid and the mixture on the upper curve that it is a point G is saturated vapor. Now, what about this region between these 2 points L and G region which are below the L, and what are the region means G means the region below the dew point curve, so that the red line below the single liquid phase, and the region above the dew curve represent a single vapor phase. So the region over here, this region is basically the liquid region, and this region is based upon a vapor region. So now the mixture at any point S on the tie line. So at any point we can consider over here on the tie line LG between these upper and lower curve. There is a two-phase mixture. So at any point between two L and G inside the envelope, there is a two phases mixture. It is vapor and liquid phase. It consists of a liquid of the component at L and vapor phase of the composition G. In each propagation, the average composition of entire mixture is represented by the S, and the relative amount of we can obtain for these equilibrium phases or that can be related with a segment of the tie line. Though, so the segment of a tie line is basically LS and GS. So the segment of a tie line, we call it as a relative relative composition.